Last time, I emphasized that if we really want to know the cause of an extinction, then we need good time control to define what events occur around the time of the extinction, and we need good sampling of the fossils to determine exactly when they became extinct. As it happens, a problem we encounter in sampling fossils is that they may not always be found where they died, at least not anymore. Fossil remains are often durable things, like teeth and mineralized bone, and these can be moved by currents, they can be buried and subsequently eroded, and they can be exposed long after fossilization to be reincorporated into much younger sediments. Paleontologists refer to these issues with fossil movement as the mixing problem. We know that the sediment record is usually not a year-by-year layer cake. Mixing occurs by burrowing animals, tree roots, erosion and redeposition, and so forth. For instance, I have a shoebox of shark's teeth and marine mammal bones from Charleston Harbor that contains fossils that are about 3 million years old. But the teeth are durable enough to be preserved on the modern sea floor. Indeed, some of my friends recently went diving offshore specifically to collect megalodon shark's teeth that are a couple million years old right on the modern sea floor. They came back with this trove of barnacle and coral encrusted teeth they found. Now, in soft sediments, burrowing clearly excavates sediment from the deeper sediment column and redeposits it on the surface. Over time, fossils may be moved a lot, particularly in slowly accumulating sediments. Now, there's this neat example of this involving a meteorite shower of glassy tektites, essentially droplets of glass made by an impact event, and an oceanographer named, fittingly, Billy Glass. He studied the distribution of impact ejecta from the Australasian strewn field, believed to be a single impact event that showered pretty wine bottle green tektites all over the South Pacific near Australia. Glass found that the impact layer made a distinctive pattern in the sediment, rather than being a single layer as you might expect for an event that lasted, say, a few hours tops. The tektite layer was distributed over 30 to 50 centimeter thick layers of sediment and had a long upward tail of decreasing abundance of tektites. Computer models can simulate this pattern as a result of burrowing activities of organisms living in the sediment. Now, initially, when the tektite layer lands on the seafloor, it is truly a thin layer of impact debris. But soon the resident invertebrates start to mix the glassy-sized sand particles from the surface deeper into the sediment column. Over time, as more sediment is slowly deposited, perhaps over several thousand years, the tektites continue to be moved around by the animals. But now the critters are reworking some of those particles upward into the newly deposited sediment. As more sediment is added, the tektites continue to be reworked upward into the new seafloor sediment, a process that continues even while some of the tektites are lost to the historic layer and stop moving around. Eventually, all the tektites wind up in the historic layer, but as a long, gradual decrease in abundance upwards in the core. The key point here is that mixing issues, like with Billy Glass's tektites, are pervasive in nature. Hence, even truly instantaneous events will usually have mixing applied to them and appear more protracted than they really were. Mixing, for example, scattered the Australasian strewn field over perhaps 50,000 years of sediment deposition, even though the actual impact was essentially instantaneous. The second key point is that the pattern of gradual turnover and gradual decline in diversity towards a boundary need not have any biological explanation other than potentially mixing. If rare species or groups like dinosaurs seem to vanish before the extinction of much more common things like foraminifera, one should be suspicious that the gradual loss of dinosaurs is just an artifact of their being uncommon. This is, of course, a frustrating situation, because if events are truly happening in an instant, the resulting fossil record is unlikely to show this. And if extinctions are protracted, we might have a hard time not just assuming that sampling artifacts are at work. Still, when we think about causes, we must always be on guard that the lovely pattern we see could just be some kind of sampling or mixing artifact. This point is hard to overemphasize since we all want the fossil record to show us what really happened. We can help ourselves a lot by recognizing the mixing and sampling issues and taking action to minimize this. First, we can work with fossils that are very abundant. Microfossils will always provide a more accurate view of the pace of extinctions than bigger, rarer fossils. Second, we can focus our efforts in sedimentary sequences where mixing is not such a problem. An obvious case is to look at sediments deposited under anaxic conditions, where the absence of benthic invertebrates reduces biological mixing. Another approach is to look at very rapidly accumulating sediments, where the sedimentation rate has swamped out mixing problems. Unfortunately, there's a trade-off here, since the faster the sediments accumulate, typically the rarer the fossils become. While mixing is fixed in such situations, sampling problems may be worse. Still, another tried and true method is to look at the same events in places scattered across the globe on the assumption that the global pattern of extinction is less affected than any local conditions. All this takes work, of course, which is perhaps partly why science has become such an increasingly an effort of groups of researchers rather than the single visionary scientist. Fortunately, it's very rewarding to work with other committed people, usually making these team discoveries much more of a pleasure than a pain.